Hello, I'm Nico L., and my master thesis was about the rendering and plausible simulation of oceans. I left most of the shading like light refractions to Unreal Engine and instead concentrated on simulating the ocean surface and preparing everything required to render the ocean to the screen. The ocean you can see here is a combination of two different simulations. A special form of the Lattice Boltzmann method is used to solve the shallow water equations, resulting in a 2D height map of a fluid. It is used to simulate interactions between the ocean and the terrain or rigid bodies. To span a preferably large domain, the simulation is performed on multiple levels of detail layers centered around the camera. Neighboring layers are connected, which allows waves to seamlessly travel through boundaries. The lacking surface details are complemented by synthesizing an animated ocean surface with the Fast Fourier Transform and wave spectra. The simulation is particularly useful to depict the ocean at different wind conditions. Rigid bodies are kept afloat thanks to a buoyancy calculation. Additionally, they can influence the fluid simulation with procedural effects applied through sphere or capsule colliders. The colliders are first sorted on the CPU and then evaluated using the signed distance between the surface and the collider. Here, this is used to apply some simple sine wave effect. The result of the Fast Fourier transform is a seamless and repeatable tile of the ocean at a certain point in time. To prevent visible repetition patterns while maintaining reasonable performance, the wave spectrum is split in multiple bands covering different frequencies. The wave spectrum is the input to the Fast Fourier transform. Wave spectra were derived from real-world measurements taken on weather ships or wave stations and date back to the 1960s. This allows to depict the ocean at different wind conditions with seamless transitions. As the name suggests, the screen space projected grid projects a grid in screen space onto a plane in the world to get a mesh that fills the viewport. A compute shader is responsible for both creating the mesh and combining all the different simulation outputs. Finally, we can send the mesh, a texture with surface normals, and foam information to Unreal Engine's renderer. And that's it. For more details on the simulation and the performance analysis, please take a look at the full master thesis, which you can download here.